I'm John Craig, and I'm originally in the field of robotics, actually. That is, robots as in factories that are spray painting cars, spot welding cars. So that was my background, and I was in that also in the academic sense, in that I wrote a textbook for the engineering field of robotics, and was a visiting scientist at Caltech, a visiting lecturer at Stanford, and briefly on the faculty at Berkeley. So I had a whole academic career in robotics. And robotics is all about joints and motion and mechanics, and as we are also animal lovers, that interest in mechanics sort of morphed into an interest in biomechanics. And so I've tried to apply the things I learned from the engineering field of robotics to horses, also cats and dogs and other things, but the horse primarily. And so if you come to our event, I'm going to try and cover some topics of kinematics and motion and joints, give you some basic background in that. People in the horse world very often talk about biomechanics, but in most cases they're really talking about functional anatomy. If you just give something a name and you say this tendon creates this sort of motion here, that's not really biomechanics, that's functional anatomy. So we'll try and go just a little bit deeper and talk about some fundamental things about biomechanics and mechanics in general. So hope to see you at our event. And so kinematics would be studying the position of these joints, how it changes, how they move, accelerations, everything. We took enough tissue off that we could place metal markers in the bones. This is all a bit too much to explain here. I will point you to a paper online where you can read our paper. Sure enough, if we look at a cat skeleton and an elephant skeleton, you'll see elephants are standing very, very upright, because for them to crouch, very tiring, whereas a cat crouches a lot. It turns out, well, why bother crouching? The cat should stand up straight too, but it turns out crouching is a very useful thing, because if you're crouched, you are ready to spring on a mouse, you're ready to flee from a predator. The elephant, if he wants to flee, the first thing he has to do is go down, kind of crouch, take the first step. So it's an advantage to be crouched if you can afford to be crouched. Now, it turns out people did experiments and they plotted all sorts of animals to see, are they really standing more upright as their body mass goes up? And sure enough, it's true. But experimentally, it doesn't come out quite as our equations predicted. And that's because my assumption that muscles are as strong as their cross-sectional area is not quite true. Actually, it turns out, it's really complicated, muscles are limited in strength by blood flow and by the way arteries branch to smaller arteries and smaller capillaries. So it's not really a square area thing, it's a complicated blood vessel branching thing. This is too complicated for us, but... So this got everyone's attention. They went, wow, what's that? And then now it's the only way to do this problem, and each year they've refined it better and better and better. And 5% is considered human performance. And we start by picking 4 points on the dorsal or front hoof wall. We place those to best describe the shape of the wall. After you pick them, you can click and drag if you need to make corrections. And it says auto label. It figures out it's a right foot lateral using the first neural network. Now it says auto calibrate. It finds the block. Now it says auto measure. Starts placing points. And this is